Good evening. I want to complete in chapter number 4 with the discussion of the periodic table, what are those that we call shells and subshells, and how the electrons are distributed in what we call atomic orbitals. The periodic chart is arranged in columns and rows. We call the columns groups and we call the rows periods. The periods go from 1 to 7 and the groups go from 1 to 18. But I prefer to use the main groups numbers from 1A to 8A because that can be helping us when we discuss the formation of ionic compounds to make cations and anions. We also observe the transition metal groups are the group B, 1B, 2B, all the way to 8B. Observe that 8B is 3 columns. We also have an insertion on the bottom that goes from here green, atomic number 57 to 58, and atomic number 89 to 90. These groups are 14 groups that do not have a group assignment. A little summary of the distribution of elements on the periodic table. We have metals, non-metals, and metalloids. And a typical example from group number 1A is sodium that we find in table salt, magnesium in group number 2A that is going to help you to go to sleep and is also found in milk of magnesia. And then on group number 7 we have halogens, chlorine that is found in Mr. Clean or Clorox. Iodine that is useful as an antiseptic when you get a cut and you clean up the cut before you place the band-aid, you use it. Helium that is part of the noble gases that we're going to find in balloons that we use for our parties. Metalloids are a good example of elements that behave, some of them as metals and non-metals, so some of the properties that can take. And one of those properties that I'm listing in here is that some of them can conduct electricity in some cases. Please remember that the groups go from 1 to 18, but I prefer to use only the main groups that go from 1A to 8A because this is useful. When we are discussing later on the formation of ionic compounds, those group numbers are going to help you to create the correct ions, all right? And then we also want to remember that these 14 groups on the bottom do not have a number. We can learn about electrons in atoms by studying the interactions of the electromagnetic radiation and matter. We experience electromagnetic radiation in different forms, such as light, the colors of the rainbow, the use of microwave or X-rays. Light is a wave with both an electric and a magnetic component. It is then the electromagnetic radiation. This can consist of particles that move as waves of energy. Have you wondered why fireworks give off different colors? For example, strontium is going to give off a red color, barium will be green, lithium is pink, sodium is yellow. And this is an indication that every element has a different energy requirement, and that can be measured. We have first the flame test that give us different color. We see copper and strontium, but that is also measured in a machine that is called the atomic spectrum. In the first case, we have the line spectrum for hydrogen that has 1, 2, 4 different values. And also we have the line spectrum of mercury. And for that, what is needed is you make a gas, let's say from the gas hydrogen, emits one light, is passed through a prism, and then after passing by the prism, it separates in colors. That was useful for the first discussion of the structure of the atom, how the electrons were distributed by Bohr. The Bohr atom theory explains well the line spectrum for hydrogen. According to the theory, the hydrogen atom has concentric circular orbits, stationary states, with certain amount of energy for each state. Emission or absorption of energy takes place only if the electron is promoted from one stationary state to the adjacent stationary state. If the electron moves within the same orbit, there is no emission or absorption of energy. Remember that electrons do not actually circle protons in fixed orbits, like a solar system. Bohr's theory does not apply for atoms that have more than 2 electrons, and because of that, it cannot explain the line spectrum for Mercury. So if we cannot find the electrons in orbits, like in a solar system, where are the electrons? They are in what is called an atomic orbital. And an atomic orbital is an answer to a wave function. This is a very complex mathematical equation, and every answer to this mathematical equation is going to give us a representation of a three-dimensional volume or a region where we can find an electron. But the electron can be in any part of those atomic orbitals. We have the atomic orbitals S, P, D, and F. So we don't pay too much attention to this formula, but we will be paying attention to the answers to this Schrödinger equation. Lines in an atomic spectrum are associated with the changes in energies of the electrons. In an atom, each electron has a specific energy known as its energy level or shell. Within the shells, electrons are grouped into subshells and orbitals. The atomic orbitals are named S, P, D, and F. The first shell has only an S subshell. Recall that orbitals are not a physical space, but they are volume or specific regions in an atom where electrons are more likely to be found. An S subshell has one orbital, a P subshell has 3 orbitals, and a D subshell has 5 orbitals. F subshell has 7 orbitals. Each one of the atomic orbitals are answers to that fancy equation I just showed you. So these are different shapes where we say the electrons can be found. The S atomic orbital is spheric, the P atomic orbital has the shape of a dumbbell, and the D atomic orbitals have the shape of a clover leaf. When it's time to fill up the electrons in an atom, they will fill in an increasing level of energy going from level number 1 to 4. It will also consider to place the electrons in the lowest energy level of the atomic orbital. S are lower in energy than P, and P are lower in energy than D, and D is lower in energy than F. S can hold 2 electrons, P can hold 6 electrons because we have 3 different P atomic orbitals. D can hold up to 10 electrons because we have 5 D atomic orbitals, and F can hold up to 14 electrons. There is not much to discuss in this slide. I just want to emphasize that we don't place 6 electrons on an P atomic orbital, all of them together. Each atomic orbital can hold up to 2 electrons only, but we have a Px, Py, and Pz. Then the same concept with the D atomic orbitals. We have 5D atomic orbitals. When we place them all together, look like this, but can hold a max of 10 electrons. So it is 2 electrons max for S, 6 electrons max for P, and 10 electrons max for D, but 2 electrons each. The wave function provides exact solution only for hydrogen. That is, all orbitals within the same level of energy are degenerated. They have equal amount of energy. The electron distribution we usually discuss is that we call the one for the ground state. That is when the atom is at the lowest level of energy. Observe the highlighted level of energy number 3 for hydrogen, degenerated, all of them are equal in energy. And when it comes to multi-electronic atoms, they are splitted. So you see 3s, 3p, 3d. Not only we see that the energy is different for each atomic orbital in the shell of the level number 3 and subshells, but also we see that the 4s is lower in energy than a 3d. Now, it is hard for us to memorize this graph, so what we do is we use that memory aid, and we will fill it up going from top to bottom, 1s, 2s, 2p, 3s, 3d, 4s, 3d, and in that order, the electron configuration will be correct. Electron configurations are described by writing the shell number or level and subshell letter in order of increasing energy from S, P, D to F. The number of electrons actually occupying each subshell is indicated by a superscript, like in this case. A graphic representation can be made by indicating each orbital as a line or a box. And each electron can be represented as an arrow. The head of the arrow indicates the spin of the electron. A shorthand using noble gases configurations is very useful for very large atoms, like you can place the number of electrons that argon has in here, just put that symbol, like in this case, and only showing the valence shell electrons. A partial diagram also is useful. In those, only the valence shell electrons are represented, like in this case. Those are the electrons that participate in a chemical reaction. So the valence shell electrons are the highest energy electrons, and those are important in determining an element's property. I want to summarize the rules assigning electrons to orbitals. Electrons occupy orbitals in a way that minimizes the energy. When constructing the electron configuration of an atom, follow the energy level diagram, but it's simpler to use a memory aid diagram. When orbitals of identical energy are available, electrons initially occupy these orbitals singly, one at a time. For example, I should not place a second electron on the first p atomic orbital x until each one of the atomic orbitals px, py, pz has 1. And I will show you that with the next slide. Let's use oxygen. Z is equal 8, so it has 8 protons and 8 electrons. The electron configuration here is following the memory 8. So we say 1s2, 2s2, 2p4. If we want to look at the spin of the electron, it's better to use the diagram. So we say here we have 2 shells. On shell number 1, which is the lowest in energy, this is when the electrons are closest to the nucleus. It has 1s2, 2 electrons with opposite spin. And then we have on the second shell, the 2s is lower in energy than the 2p, is also complete. When we complete those first 4 electrons, we have 4 left. And because we have 4 electrons, we first fill it up singly, what you see in black arrows, and the very last electron now needs to be paired up. When we are pairing this up, Now we need to place that with the arrow on opposite direction to indicate the spin of the electron. We also have the condensed formula where the inner electrons, those that are on the lowest shell, are represented by the symbol of the noble gas helium. The 2 electrons of helium are in 1s2, so we just place the symbol. And this is very useful when we have large atoms that I will show you on the next slide. I'm going to show you how simple it becomes once you have practiced the full electron configuration. Once you know how to do the full electron configuration, we use the condensed electron configuration by placing the inner electrons in a bracket using the symbol of the noble gas that precedes that atom. For example, for chlorine, we are going to have 17 electrons, so the 10 electrons that are in the inner part of the atom are identical to the electron configuration of neon. So we're going to place the symbol of neon indicating that we have 10 inner electrons, and we only need to place right next to it the outermost valence shell electrons. We also then continue for 18, and we are reaching another noble gas. In one of the slides, I already showed you that for the electron configuration of potassium, that was atomic number 19, we have 19 electrons, and we place the argon in a bracket for the 18 electrons, and the outermost electron shell for potassium was 4s1, and that was sufficient to indicate the full electron configuration.